Good morning, everyone. Welcome to Turbulence again. We are going to cover the last chapter in this video series, which is model evaluation. The first question that comes is, if you do some modeling, is it accurate or not? Is it correct or not? So the literature takes modeling seriously, but always with a grain of salt. Whatever you say that you found running a turbulence model is not believed until you show some experimental evidence or observation evidence and some level of agreement between your model and the observation. That's the only way to make a case a model is a good model. And this chapter is going to teach you how to perform such model evaluation. That means against experimental observation. So, let's talk about verification and validation. Have you seen these two words before? For example, what is the difference between verification and validation? Okay. Looks like we haven't seen it. So, yes.
I think validation is something, for example, you check time series is following the trend of the time series you are predicted with your model, something like it, the results of the model and observed results, but verification is matching them together.
I like the first part that you said. Verification is just checking that you are solving the equations right. You know, it doesn't say anything about comparing to experiments. So yeah, there are two different things, but both are required to demonstrate a model being useful. So let's underline a few sentences here. One of the main pillars of numerical simulation is the validation and verification of the calculation performed using a specific code or technique. Validation is the process of solving the right equations for the simulated physics, while verification is solving those equations in the proper manner. And I'll give you a very fun example of this in a moment. So, based on the two definitions, one cannot validate a whole numerical code, but only a specific set of calculations for a case study performed using the code. Let's use that example. Validation. Velocity is given by distance divided by time for a particle motion. For a particle motion, for example, V is equal to dx over dt. which means that I'm verifying, or should be careful with terminology, I'm assuring I'm using the right equation for the physical phenomena. If somebody asks me to calculate velocity, this is the equation I should use. So validation is using the right equation. Okay. Of course, there is comparison with observation too. So you use this equation, you get some answer, and then you compare to the measurement. It goes without saying. But verification is something different. Verification is given that, say, dx is equal to v dt, and if dx is 2 meters, if v is, let's say, 2 meters per second, and if dt is 1 second, I make one claim. So claim 1, or say model 1. X is equal to 2 times 1 is equal to 2 meters. I make another model, that's model 2. And I find that x is equal to 2 times 1 is equal to 1 meter. I made 2 models. Well, I already know I'm using the right equation, okay? But am I solving this equation right between the 2 models? Well, in the first case, I am. I'm solving this equation correctly. X is equal to v dt. 2 times 1 is 2 meters. This first model is verified. This second model is not verified. Even though I'm using the right equation, I'm not solving this equation right. So that's something to demonstrate. I can also put a nice catchphrase. So validation is solving the right equation. Solving the right equation. Verification is solving the equation right. What a nice way to remember this. Yeah. And I learned it from a grad student. Very brilliant one. Okay, let's talk about time and space discretization error estimation. If you do numerical modeling, you solve some sort of equations in discretized time and space. I mean, we live in a world comprised of time and space, so whatever equation we solve, we discretize time and space domains and solve those equations. Discretization convergence is an analysis that must be performed for most complete models of turbulence, such as K epsilon, that are solved numerically. However, although informative, this analysis is not necessarily conclusive when applied to incomplete models, such as the LES or mixed model. So see, I'm saying something about convergence as a result of discretization This has only meaning if you are using a complete turbulence model, which means that if you make your discretization finer and finer and finer, if you make your grid more and more and more small, grid elements, eventually your equations converge to a solution. Only for the complete models though. If you have incomplete models and you refine your discretization, there's no guarantee the solution will converge, such as the case with LES model. Remember, because the equations depend on the grid spacing in the first place. So the whole numerical system will change when you refine or coarsen the grid. In other words, don't attempt to show convergence for an incomplete model. It's wrongdoing. Don't do that. The spatial and temporal discretization of a model domain is a crucial component for numerical simulation. The number of time steps or grid elements, say nodes, which can be created in one domain may vary significantly depending on the time march sequence, the size of that domain, and the size of the grid elements themselves. As a numerical solution of the governing equations is obtained for each time step and each spatial element or node, the number of time steps, elements, or nodes and the way they are arranged in the grid can notably affect the accuracy of the numerical result. Let's say space discretization. Say I'm looking at space discretization in 2 dimensions. Space here's my domain. Let's say a 2D domain for a boundary layer flow. I can come up with a very coarse grid or I can come up with a very fine grid. So you see the space discretization is different for 2 grids. And if I try to model, run or solve my model on each of the 2 grids, I may get different answers. So it matters the way the grid has been discretized. Is it defined as a coarse? Even the shape of the grid. Let's say here I'm slicing it vertically. But let's say I had sliced this horizontally, right? It all affects the solution. I can say the same thing about time discretization. Time discretization. Here I'm considering an arrow of time. Let's say I start from time 0 and I finish at some final time. I could have a very coarse time step in my model, say delta t, or I could have a very fine time step in which delta t is much smaller. So I'm showing you 2 different ways of discretizing the space and time domains. How would you assess a solution then run on any given grid? So now we're going to tell you how to do that. The most simple test is applied for spatial discretization, where a procedure is performed for quantifying the degree of independence of the numerical solution from the grid size and configuration changes. This is called grid independence test. This is simple to do. The grid independence test is usually performed for 3 levels of grid fineness: coarse, medium, and fine. The methodology that is used for grid independence testing consists of a comparison between the obtained solution, whatever it might be, velocity, temperature, momentum, concentration, on a continuous spatial segment such as a line or surface for each grid level. The grid level that exhibits enough grid independency for a solution, that means does not show a significant change in the solution, is then considered to be a converged solution. Okay? So you just make 3 levels of discretization, run your solution, and then you get your answer. I'll give you an example here on the side. Let's say I have a coarse grid. In which the mesh is very coarse. I have a medium grid. I refine this a little bit. And then I have a fine grid. So I have 3 levels of mesh, say 1, 2, 3. Suppose it was a boundary layer flow, very simple flow, and then I plot any solution that I care about on a vertical line. For example, I could plot the solution on this line, which I am showing by dashed line. Of course, flow is going from left to right. So flow is going this way. I'm interested to know the mean velocity as a function of height. This would be y. Suppose on the coarse grid I get this answer. Suppose on the medium grid I get this answer. Of course, I'm deliberately showing a discretized answer. And suppose in the fine grid I get that answer, right? So I got answer 1, answer 2, and answer 3. And I'm observing that answer 2 and 3, simulations 2 and 3 performed on medium and fine grids are very close to one another. Certainly on that line, because this was the line of interest. So after doing this test, I'm now assured that I have, I'm getting a converged solution. Okay, so that's what a grid independence test is. Just run it on 3 grids, see if you're getting closer and closer, sort of asymptotically speaking. Sometimes grid economy is considered in the independence test. If a finer grid shows no considerable change in the solution than a coarser grid, then the latter is independent enough and is chosen to accelerate the solution process for further study. Okay, so which means like grid 2 is very close to grid 3. I may even be tempted to use grid 2 for my analysis because it's very close. If I did choose grid 2, I would have an economized model. It's not too expensive to run. But I shouldn't use number 1. Okay? However, we don't stop here because the error theory and sort of theory around order of convergence of a solution has been much more developed than I explained. So if you want to do a better job, if you are, let's say, writing a good article or thesis, then you need to do a little bit more. So let's show you how to do that. Let's talk about order of convergence. Order of convergence. The order of convergence involves the behavior of the solution as the difference between the discrete solution and the exact solution. In a way, it tells you how fast you're approaching the exact solution by refining your grid further and further. Okay? You might be approaching twice as fast, 4 times as fast, 8 times as fast, even 1.5 times as fast. The first thing you calculate is this difference, error, which is the difference between the numerical answer and the exact answer. So if you like, this is the numerical answer. This is exact. For many simple problems, there is an exact answer, right? Suppose x is equal to vt, right? For a simple modeling system, sometimes there is an exact answer. But numerical answer depends on the grid or a space discretization. We are going to treat this as if an exact answer is always available. Okay? Suppose you're only talking about complete models. There should be some exact answer, right? There should be something. Because every complete model should converge. Well, what is the difference then? What is the error between numerical and answer and the exact? Well, if you can show that this difference is equal to constant c, a measure of grid spacing to the power p, and some higher order terms you may neglect, then you can say the order of convergence is p. Why am I saying order of convergence? Think about it. Okay, neglect the higher order terms. Let's say my grid spacing is 1 meter. And suppose C is 1, okay? And P is 2. Then the error for a grid of resolution 1 meter is just 1 to the power of 2 is 1 meter. Or say this was meter per second, you're talking velocity. Suppose now I make my grid 1/2 of a meter. So 1/2 of a meter to the power of 2 is 1/4. See, the error is now gone down by a factor of 4. I halved the grid spacing, but the error went down by a factor of 4. So this power P determines how fast the error would go down as you refine the mesh. That's why it's defined in the very first place using a power relationship, h to the power of P. Okay? But there are some problems here. The first problem is that you don't have an exact answer usually to begin with. So that's an unknown. So that's the first problem. The second problem is your mesh does not necessarily have uniform spacing. We have looked at a lot of meshes that are, suppose, more resolved near a wall and coarser in the higher locations of the domain. So that's the second problem. Well, the second problem is easy to deal with. You can actually calculate a representative mesh size. In a way, you can calculate an average discretization. Suppose you have a control volume system, so you have a lot of blocks or slabs. You have a lot of blocks, like 2,000 blocks in your mesh, and these blocks have different volumes. Well, what's the average size of all these blocks? Well, you add all the volumes together, find the average of the volume, divide by the number of blocks, and then take the cubic root. This should be the representative cell size for the whole thing. It's one number for the whole mesh, even though the mesh is variable in the grid size. So this works for control volume schemes, pretty nice. Although for finite difference schemes, which we have in the computer labs, the representative cell size can be defined in a similar fashion. So in the finite difference, well, we actually have difference between the nodes, or spacing between the computational nodes, and you take, let's say, the average distance between adjacent nodes as your representative mesh size h. So just remember the assignments, computer assignments, are finite difference schemes. Likewise, for finite element schemes, you can define some sort of mesh size. I must say that even though most models out there that you use in 3D are control volume, like Fluent, Star CD, and OpenFOAM or control volume, but there's a lot of simple models out there that are finite difference, easier to sort of understand and develop the theory over. And that's why I chose finite difference for this course, because this was not supposed to be a very intensive computational fluid dynamics course. This is theoretical fundamental course. So I think choice of finite difference was the best choice to demonstrating the theory of turbulence and some of the applications. Okay? Maybe you need a picture too. Of course, I can provide a picture to you. The very boundary layer we're talking about, right? I mean, think about it. The boundary layer we talked in the past could have different resolution, right? The question is, what is the representative mesh size? So you can get the representative mesh size by summing all the volumes, finding an average, and then taking the cubic root. So if you like, for this mesh, it's neither as big as that cell or as small as that cell, but sort of, it's kind of in between. So that's H, representative of the whole thing. Same concept exists over time. I mean, you might think a time march may have variable time stepping, right? In fact, the time stepping can change. You might have a very small time step here, and then you might have a large time step here. Likewise, you can take the average of all these time steps and calculate the representative time step. A lot of models out there do that. They offer the flexibility to the user. For example, their time stepping is variable. So the model can simulate the transient process as fast as possible without converging. So it gradually increases the time step until the solution behavior gets iffy. And if that happens, it reduces the time scale again. So kind of dynamically adapts the time step. Okay? It's like an automatic car, right? You start driving, the car decides what gear to shift to. So it comes with pros and cons, of course. I prefer a standard. Okay. Going back to the error equation, a second order discretization for either space or time means that this order of convergence is equal or at least close to 2. The second order is good. I mean, if you do serious computational work, you're probably second order and above. If you develop codes that are first order, there's not much demand out there for it, and if you submit a paper with first order convergence, sometimes the reviewer may say, you can do better, so they ask you to revise it substantially. So try to look out for first order schemes. Go at second order schemes. Go for first order of convergence schemes only if you must or you have to. Above second order, there are also third, fourth order. There's some fantastic schemes out there, but the numerical stability becomes sometimes a question for those. Like a fourth order scheme may have a very unstable numerical behavior. A numerical code uses a numerical algorithm that will provide a theoretical order of convergence. However, the boundary conditions, numerical models, and the mesh will reduce this order. So it will likely be lower. So here what I'm saying is that even order of convergence, there's no theoretical order of convergence you can calculate. It's an approximation. The only way to know is to run a model for different meshes and calculate the order of convergence. That's the exact way to do it. For example, theory may suggest is 2, but when you calculate it, maybe 1.8 or 1.9. For a variety of reasons. The boundary conditions reduce the order of convergence, the algorithms. A lot can happen in the code to reduce this. But let's say how you would calculate order of convergence. Suppose you neglect the higher order terms. If you did that, then you can express the error in a linear format, taking the ln of both sides, which suggests that the ln of error is now linearly related to the order of convergence. So the ln of E with respect to ln of discretization exhibits a slope of P. Of course, ln C then becomes the intercept. Okay? Which means something like this. If you plot a bunch of simulations and you plot ln of H over with respect to ln of E, so each point is one simulation, right? You may simulate a bunch of points, a bunch of resolutions. This may be something you may get. So if you fit a line to those simulations, the order of convergence would appear as the slope of that line. So again, I'm showing you how to find it experimentally. Using numerical experiments. That means every time you have to change the discretization and rerun the model, you get 1 point. Coarsen it, run it again, you get another error. Coarsen it, run it again, you get another error, right? So every point is the entire solution obtained by coarsening the grid this way or refining the grid that way. So it can be found by tests. The order of convergence, P, can be obtained from the slope of the curve of ln E versus ln H. If such data are available, the slope can be read from a graph. You might do least squares fitting or something like that. There's a faster way to do it too. A more direct way for finding P is obtained by 3 solutions. So you don't actually have to run it like 20 times, the whole model 20 times. You actually need 3 solutions only to be able to calculate. Suppose we select 3 significantly different sets of meshes and run our simulations to determine values of one key solution, right? Let's say you care about momentum at a particular time at the exit of a jet. Your model solves for momentum. At a strategic, you have a spray paint, right? So you're painting some surface, you design a spray, and you model flow of paint, and you want to know the velocity of paint as it impacts the surface, right? It's just one number. You make the mesh for the fluid, like the nozzle and the fluid domain. You suppose you use it on 3 different meshes. So by the way, so phi here is the solution. This could be the momentum at the point of impact. And the 3 meshes are H1, H2, H3. They represented the cell sizes. And suppose this was the finest mesh. So this is fine, this is medium, this is coarse.
Then we define the mesh refinement ratio, which means that it's the ratio of two adjacent levels of mesh sizes. So H3 over H2 is the refinement ratio. It could be 1, 1.5, 2, whatever it is. But suppose it's the same between H2 and H3 and H1, H2. I mean, suppose that you have a constant refinement ratio. And further, the difference between the solutions, these are some sort of absolute error. So two adjacent mesh sizes, 2 and 3, you get a different relative error between the two solutions, or absolute error. Yeah, so it's the difference between the solution you obtain. Let's say it's this nozzle that I have that impacts paint on the surface. On one mesh it gives me 2 meters per second. On the next mesh, it gives me 2.2 meters per second. The difference between the solutions that I obtained was 0.2 meters per second. This I know as phi mn, or phi m minus phi n. I can do this calculation comparing mesh levels 2 and 3, or I could do this comparing mesh levels 1 and 2. It's up to me. If using a constant mesh refinement ratio, then its order of convergence is easier to define, and this is it. So all you need is refinement ratio and the absolute errors between two adjacent levels of mesh. If you put that in this equation, you get order of convergence. That means you run the nozzle study 3 times on 3 levels of mesh, and you can calculate P. What's fascinating is order of convergence can be different in different areas of the domain. Let's say if you calculate this near a boundary, it's less, because boundaries are not numerically efficient. But if you calculate this in the middle of the domain, then it's higher, usually. So boundaries reduce order of convergence. It may be 1 there, it may be 2 in the middle, sort of sum over, it may be 1.8. The order of convergence is determined by the order of the leading term of truncation error and is presented with respect to the scale of discretization H. The local order of convergence is the order of the stencil representing the discretization of the equation at one location in the mesh. For instance, interior boundary conditions, locations. The global order of convergence is considered as the propagation and accumulation of errors outside the stencil. It's a very technical sentence. This sort of propagation causes the global order of convergence to be less than the local order of convergence. The order of convergence for the boundary condition can be usually 1 order lower than the interior. However, without degrading the overall global convergence significantly. Can anybody explain why? Yes, the online viewer was right. I heard you. Because, let's say for any boundary element or boundary patch, you get many tens or hundreds of patches inside the domain. Right? Think about it. If I slice up this room into 1 million cells, only maybe a couple of thousand end up being the boundary cells. The majority of those cells are internal cells, right? So the internal cells are usually way more than the boundary cells. You can even accept my claim looking at here. Let's say for this mesh, I only have 1, 2, 3, 4, 5, 6 boundary cells. But the rest of the cells are interior to the domain, which could be sort of maybe 25, something like that. So it's always true. So don't worry about lower order convergence near boundaries too much. That's okay. This is due to the fact that in three-dimensional geometries, boundary cells are outnumbered by interior cells. That's what I just said. Getting very close. Assessing the order of convergence of a code and calculations requires one to sufficiently refine the mesh such that the solution is in the asymptotic range of convergence. The asymptotic range of convergence is obtained when the mesh spacing is such that the various mesh spacing edge and errors result in constancy of C. Let me try to show a picture. I think you can show a picture. Say your grid is very coarse. It's very coarse. If you have a very coarse grid, you will get, if you calculate order of convergence, you get one intercept. Let's say you refine the grid further, but it's still not fine enough. I should show with a different symbol. Say I used circles before. Now I use rectangles. If I calculate an order of convergence, I may get a different C, right? You see what I'm saying? I get, let's say, ln of C, triangle, ln of C, rectangle. But C will be constant if I refine this enough. If it's refined enough, then the more and more I refine my mesh, then the more and more I will find the same C. So you see the plot is very scattered and noisy for very coarse discretization, but for very fine discretizations, it should get close to a line. So you never want to build a model which is in this region. You always want a model to be in this region. That's maybe another way to guess if your discretization is good enough. I mean, calculate this, keep calculating this, and make sure you get the same C. Okay, I still haven't addressed the situation with not having an exact solution, and so this next thing is going to touch on that one. It's called grid convergence index. So this is some other type of index which is more professionally used in turbulence modeling. This is the next level beyond grid independency test. GIT. GCI, grid convergence index, is more commonly used. And let's define it for you. A representative measure for grid refinement studies was proposed by Roash. Well, was one of the sort of people who did really fine work on this. So proposed the GCI. It's actually come from a very rich extrapolation theory called Richardson extrapolation theory. So it's very math intensive. Not for the practical engineer or scientist. So we're not going to derive it, we're just going to show it to you. Which uses an asymptotic approach for calculating the amount of uncertainty in a grid convergence. It tells you how close you are to a hypothetical exact solution, which you don't know what it is, but you know how close you are to it. For example, I can tell you you are within 5% of the exact answer, or you are within 4%, or we are within 2.5%. It tells you how close you are, but it doesn't tell you what the exact solution is. Similar to the simpler grid independence test, the GCI makes use of the solution on 3 different grid size levels, which we introduced before. So you need 3 levels of discretization. The GCI reports a numerical value that shows you how much convergence is achieved in the solution between 2 successive grid levels, or between the courses grid level taken as reference and each one of the 2 other grids. It's a comparison type analysis. Or if you like, marginal improvement, relative improvement by refinement. A consistent numerical analysis is one which provides a result approaching an asymptotic value as the mesh resolution approaches 0. Thus, the discretized equations will approach the solution of the original differential equations. One significant issue in numerical computation is to decide what level of mesh resolution is appropriate. There is no universal answer that you must be within 10% of the answer, or you must be within 5% of the answer for the answer to be acceptable. Depends on the situation. I mean, if you are, say, designing a sensitive medical instrument, I mean, the accuracy is pretty low. Let's say dental, like you're designing a watershed for dental applications. You want to be within 1%, right? Or else the health is in danger. But let's say you are developing some low-cost spray paint technology, sure, you can be within even 20% of the answer. Also, how much resources you have, how much computational power you have, how much knowledge you have building and using a model. It's all a moving target. So function of flow conditions, type of analysis, geometry, and other variables. One is often left to start with a coarse mesh and then conduct a series of mesh refinements to finally decide where to stop. So you start with a coarse mesh because your model is possibly going to run faster, quickly gives you an answer, you can verify it at least, and then you gradually refine the mesh until you stop where the error is below some given required value. That's what we do all the time in our lab, right? When we test our solvers, we always test them on coarse grids first and then move toward higher refinements. One must recognize the distinction between a numerical result that approaches an asymptotic value and one that approaches the true solution. Remember, I'm not saying the asymptotic solution is the true solution. The asymptotic solution may be off from the true solution a little bit, right? So these are 2 different things. Even when the asymptotic solution to a set of differential equations is found, it may be different from the physical solution. So keep that in mind. The grid convergence index is a measure of the percentage the computed solution is away from the asymptotic solution. I already said that. It indicates an error band on how far the solution is from the asymptotic value and how much the solution will change with a further refinement of the mesh. Again, it only tells you how close you are. A small value of GCI indicates that the computation is within the asymptotic range. So how do you calculate GCI? All you need to know is a safety factor Fs multiplied by a relative error divided by refinement ratio raised to the power of order of convergence minus 1. So you calculate GCI between two adjacent levels of mesh and you plug in these numbers. This Fs is a factor of safety. It's thrown in to be conservative. The refinement may be in either space or time. So GCI is a general concept. It's used only for, not only for space discretization, but also for time. And it needs to be a combination of space and time discretization. So factor of safety, usually you take 3 if you have 2 levels of mesh, or you take 1.5 if you have 3 levels of mesh to consider. The relative error, epsilon, between 2 different levels of mesh is defined as usual. I mean, many of us have used this relative error. Further, it is assumed that the mesh refinement ratio is applied equally in all coordinate directions, even for time. Remember I said the refinement ratio is can be direction dependent. I'll give you an example. Let's say I have this mesh. Okay, so in the x direction I have 2 elements, right? In the y direction I have also 2 elements. Then I slice this equally more in each direction. See what happened? So now refinement ratio in both x and y directions is 2. Agreed? So R is given a definition is 2. Let's say Rx is 2, Ry is also 2. But not always. I could have a case where I refine only further in the x direction. I don't refine in the y direction. In that case, refinement ratio is more complicated. It depends on the direction you're talking about. But let's say you kept the ratio the same for a space and time. Then the grid convergence index you calculated is for all. Okay? This is the overall grid convergence index. However, if your grid is not refined by the same amount in different directions and time, then you can calculate GCI for each direction independently and then add them up. So in other words, you can calculate GCI independently in the over time discretization, direction x, y, and z. Okay? You might imagine that most possibly you calculate a larger number, making sense because if you simultaneously refine in multiple directions by the same amount, you should get to your answer faster as opposed to only refining in the x direction or only in the y direction. But the nice thing about the theory is it's very generalized. You can apply it as you wish. Finally, I should say some things about incomplete models. It must be noted that the concept of grid refinement or grid convergence does not always apply to models that are not complete or incomplete, such as mixing length and LES. We already said that those models depend on mesh density, choice of mesh or grid. They have formulas in them that depend on the solution itself. Like mixing length depends on the gradient of velocity. For example, for the algebraic models, in such a case, GCI does not necessarily guarantee to approach to 0, or you might even find GCI will shoot up as you refine your mesh beyond a further resolution. So don't do this. You don't have to calculate GCI. If you want to see the sensitivity of your solution to the mesh, just change it, run the solution, and look at grid independency test. GTI. Don't use GCI for incomplete models. And we have again and again verified this in multiple studies that have happened. Okay? In other words, incomplete models do not guarantee a converged solution. They may be better than a complete model, but the concept of convergence does not exist. Sounds like quantum mechanics. You just want to squeeze an answer out of it, but it's like, anyway, it's not fully predictable. Any questions so far? I have not yet talked about comparison to observations yet, but that's what I'm going to do next. What about observations? How do I compare my model result to some observed values? Observation and model error quantification. So I'm going to show you how to do it. Error quantification between the experimentally observed and measured quantities and the numerically predicted quantities is performed in various ways. Most commonly, the simple absolute error, just difference, is quantified and used to report the amount of error between observed and predicted values, with the observed quantity usually used as the reference. Okay, so the phenomena I measured was 2 meters per second. The model gave me 2.2 meters per second. The error is 2.2 minus 2 is 0.2 meters per second. It's an absolute error. However, this method may yield some exaggeration. Alternatively, people defined more exotic measures of error, known as fractional mean bias and normalized mean square error. Suppose that you have a bunch of observations, phi O. Phi O is a bunch of observations, and phi P is a bunch of predictions. I mean, P for model, right? So O for observation, P is for prediction, for model. You can calculate the average of the absolute error. Remember, I'm putting angle bracket to signify taking average. And then I divide by the average of both observation and prediction. It gives me a fractional bias, okay? Because I am somehow normalizing error. Same thing about normalized mean square error. So I look at the variances of the differences, right? And then I divide by the product of the mean values of observation and prediction. I can show examples to show you how this works. So phi O, phi P are the observed and predicted quantities. Unlike the absolute error, fractional bias and normalized mean square error define some specific attribute of the calculated error. Overall, the bias shows how much shift there is between predictions and observations, while NMSC or mean square error shows the spread of one values with respect to the other. For a perfect model, both of them should be 0, but it's never the case. Okay? So bias shows you what's the shift between the model and the data. NMSC shows what's the spread or scatter. This is only useful when none of the two quantities approach 0, because you could imagine you can never divide by 0. So be careful. Don't use this where either observation or model may approach 0. I mean, if the quantity of interest is your model is predicting temperature of water as it freezes in Celsius, right? Water freezes at 0 degrees. And that's the model you're trying to build. to predict 0. Don't use fractional bias because you don't want to be dividing by 0. So be careful. Never use this. If you have to divide by 0, or if the prediction observation is close to 0, then use absolute bias, not fractional. We learned this the hard way after months of simulations and disappointments. Why is my error so large? Oops, because I'm dividing by 0. Don't do it. Okay, so let's put some I put a nice picture. I want to do it here. So this concept of bias and NMC. So fractional bias versus normalized mean square error. Suppose that I'm measuring a transient process. Observation is the dashed line. Prediction, is the solid line. Prediction or model is the dashed line. And I'm looking at my solution versus time. So here is the observation. Could be anything. So I have some phenomenon, physical phenomenon that some solution or some observation peaks over time and then goes down. I don't know, let's say I turn up the thermostat and I measure temperature in this room, temperature goes up, and then I turn it down, temperature goes down. And then I build a model, and the model may do a pretty good job in predicting this. Well, it won't exactly predict the same phenomena, but by and large, the model is a pretty good model. If I calculate the fraction of bias, it should be very low. NMSE should also be low, because there is no systematic shift between the two, and there is no scatter between the two either. But suppose I build another model, and this time the model gives me this. It's capturing the trend, but it's shifted. So if I calculate some sort of a bias, fractional bias, this time it's going to be high. So is NMSE. And NMSE. So is NMSE. It's going to be high because there's still a scatter between observation and model. So first of all of the model predictions are shifted upwards. There should be a bias here. Also, every pair of measurements, there is a difference for every pair of measurements and predictions. But a lot of interesting things can happen. Suppose next time you build another model and it gives you something like this. So the model sort of predicts a lot of unphysical fluctuations. This could happen. Can you tell me if bias is low or high? Is bias in this low or high? Anyone? Is there a systematic shift between the prediction and observation? Low. Systematic said it's low. There's no systematic. But what about NMSE? This is high because there's a lot of scatter. Another scenario. I mean, you could have a model which starts to over-predict and then starts to under-predict. What about here? Is bias low or high? As usual, the online viewer is right. It's low still. Because
sure, it's up here, but it's being compensated by being down here. So the up and the down cancel each other. It's still low. NMSE is still high. And the worst situation one might get is the model cannot do anything. Imagine it's consistently, systematically shifted. It's also very scattered and noisy. So this is the worst type of model you can build. The fractional bias and NMSE are both high. So it appears that if you want a low NMSE, bias should also be low. It's impossible to get a low NMSE and a high bias. So bias should be low in the first place to get a low NMSE. In terms of modeling, we care more about NMSE. Because if you have a systematic shift in any solution, you can just add or subtract the constant and get close. So bias is easier to fix, but NMSE is more difficult. So in a lot of large scale environmental modeling work, like atmospheric modeling, ocean modeling, space modeling, they care more about NMSE. If they have a bias, they don't worry too much because you can correct bias very easily. Okay, so some demonstration there. And really, finally, there's only one problem to do, left to do in this chapter. So I want to do problem 2 in this chapter. Problem 2. Any questions before I do that problem? Very short problem. I think this came from an exam, maybe. Assume that the order of convergence for a discretized model is exactly p equal to 2. Show that if the resolution of the discretization is increased by a factor of 2, i.e., the finer level of mesh is 1/2 size of the coarser level of mesh. Then the discretization error is reduced by a factor of 4. In other words, error 2 divided by error is 1/4 of error 1. And we can basically show that. Example 2. By definition, error can be defined using order of convergence. Usually, practically, we neglect higher order terms. Then, ratio of two errors is the ratio of CH to the power of P. Of course, the C's cancel, so you're left with the ratio of refinement ratio, if you will, to the power of P. And in this case, refinement ratio, it was 1/2, and order of convergence is 2. So you get 1/4. So E2 is 1/4 E1. Okay, so that is the example here. Any questions? Okay, so we have finished the all sort of the substantial juice of the course. In the first half, we talked a lot about theory. I think it was a very dense and rich first half of any course. Lots of math and physics explanations, lots of interesting computer labs, and then we switched over to modeling. The modeling part was a little shorter, although modeling turbulence is a huge field. In fact, there is no unified theory of turbulence or theory of modeling of turbulence. It's a huge, scattered field. I mean, think about it. If we have reached amazing success in, let's say, quantum mechanics. If you want to predict the width of North America, quantum mechanics can do it for you with the precision of a width of a hair. It's how accurate it is, right? And it's a relatively new field, 6 to 7 years. Turbulence is older. I mean, we've been struggling with this stuff since we've been doing engineering. It's a couple of 1,000-year-old problem. Still, there's no unified theory. There's lots of wild guesses and constants people bring out of their pockets and close these equations in all kinds of nonsensical ways. They get an answer. It's mostly an approximation, lots of errors involved. So it's a really, it's a field that's classically was unsolved, and it's still unsolved, and maybe continues to be unsolved for the next couple of 100 centuries. Hopefully, one ambitious or a few ambitious people can come up with a unified theory and sort of close the deal. But it's notoriously difficult. It's a very difficult problem. If you're ambitious, you can pursue entire careers in turbulence theory and modeling. There's lots of prizes out there. You get Nobel Prize, Fields Medal. So lots of work to be done. Anyway, let me talk briefly about applications, and this is just soft talk. Okay, so that's part 3. Really soft talk, and I'm going to do this in 5 minutes. So in terms of engineering, turbulence theory and modeling is used all the time in engineering. Maybe many of you are engineers here. A lot of sort of industrial chemical processes, sort of liquid extraction industries use it. Like people in water purification sort of technologies and research do this all the time. Separate fluids and things like that. Lots of food industries rely on this. Coalescence. Also, it's a device that divides an emulsion into specific components. And again, its emulsion is all over practical engineering. Often flows are turbulent in highly industrial cases. Wastewater treatment is another one. Process of mixing is really huge in wastewater treatment. Again, understanding turbulent flow regimes in these systems are crucial. Desalination, right? I mean, fresh water is one of the most scarce resources out there. Lots of technologies there try to get fresh water out of salt water. Desalination. It relies on this. You have to obtain water from the oceans, design membranes. A lot of the time the flow is in the turbulent regime, so you have to understand flow in these desalination systems. And combustion devices all over the place. I mean, in combustion, you actually need turbulence, like in gas turbines, jet engines, rockets, cars, motorcycles, everything. Because the way you can burn a fuel and get power out of it is by mixing it, right? So combustion engineers are all over turbulence studies. Huge. Indoor ventilation, I mean, buildings, right, consume 40% of energy in the developed world. That's a lot of energy flowing into the buildings. The air you're breathing is in the turbulent regime. People who design ventilation systems, heating, cooling systems for buildings are struggling, developing with
developing turbulence theories and models to design buildings in the proper way. My PhD was also in building ventilation, so that's where I learned a lot of the stuff. And then aeronautics. Well, they've been doing it for a long time now, designing airfoils, the sort of aircrafts, and all of those things, rockets, space exploration. There's a lot happening, and it gets into even more uncharted territories of compressible flows and supersonic flows, and it gets really fun. There's shock flows that people study in combination with turbulence, and of course the renewable energy. Like in this room, people design renewable energy systems with wind turbines and Archimedes screws and so on. I mean, the list goes on. Okay. Further, at larger scale, if you talk to the science communities, scientists deal with this stuff all the time. The first one is meteorology. In fact, a lot of the theories we know and developed originated from meteorology. Like people like Pranto, Richardson, Deerdorf, they were actually studying weather that they came up with those theories, which later engineers used. Pranto was an engineer in the first place, though, but he was, for some time, was studying weather. Like the large eddy simulation all started from meteorological applications. So this is huge. And atmospheric turbulence is part of climate change, part of air pollution. It's a big deal, right? So you have to do a good job so that these models work correctly and you can make some useful prediction or weather forecasting, things like that. Lots of amounts of liabilities and government policy decision making, big decision making that depend on how good we can develop air pollution, weather forecast, and climate models, and turbulence is part of it. Oceanography, right? I mean, there's some examples like ocean systems. 70% of the Earth is water. Okay, so if you want to know how the Earth works, you have to understand ocean currents and ocean movement. Oceans play a huge role in absorbing CO2 from the atmosphere. So they recycle CO2. They control greenhouse gas levels in the atmosphere. Oceans are a huge player. They play a huge role in thermal balance of the planet. Like they bring cold waters from the Arctic and then warm waters from the lower latitudes, and they balance the energy of the Earth. There is also vertical circulations of transporting nutrients and the fish systems, and they drive entire hurricanes and tornadoes. And, this ocean is also a big part of it, and a lot of the theories, applications of turbulence is in oceanography. And if I don't stop there, there is also a space predictions of turbulence. You've heard of the solar flares, right? The solar winds. The sun makes these winds. It's a blob of an eddy of the solar surface that bursts and sort of makes harsh weather in the solar system. So people study that. There's actually solar flare forecasting. If you didn't know, there's forecasting, and they study and then they advise the power grid or whatever. People study weather systems on other planets. People run models of meteorology on Mars and Venus and the Titan and the moons of these other planets in search of life. What is a proper weather system for life to exist on another planet, right? So people run these weather models. You can run them. Also, star formation, the gas clouds and things like that. These are fluid systems out there. So people out there build turbulence models of space systems, and that's an exciting field. So really, in my opinion, if there is motion at large scale, there will be turbulence. That's how general it is. So the only places that you may not have turbulence is really small scale systems of like an atom, like really small scale, like flowing really tiny systems, micro nano fluids, and maybe quantum mechanics. You don't have turbulence in there because you're talking about the size of an atom. But if you study any other larger system, then there's flow, there is instability, there's mixing, and there's turbulence. That's how wide-reaching it is. So hopefully that can inject excitement into your careers, and hopefully you pursue some of these nice problems and find nice answers. So I'm done here in lecturing formally. Is there any questions about the material so far? Okay, good. Thank you so much for your patience and sitting through the material. And thanks for the online viewers to following the video series. Please leave us comments. Yeah, so we will then see you next time.